Good morning. This is Badri Younes. I am the Deputy Associate Administrator and the Program Manager for NASA's Space Communication and Navigation Program. I'm so happy to be here with you today to talk about optical communications. NASA considers optical communication as a strategic objective, as a critical capability needed to support future mission requirements. Before I talk about what we are doing in optical communication and technology, I'd like to give you a snapshot on SCAN. What does SCAN do for the agency and its place within the agency in terms of enabling human space exploration and science missions? We work actively on developing and operating as well as managing all of NASA's space communication capability. We work on advancing the technology such that we can meet future mission needs and enhance future mission experience in this in acquiring their data and in commanding and controlling their spacecraft. We work internally and externally to optimize the utilization of spectrum. Spectrum is a commodity that has been in high demand recently. There is a strong contention for spectrum in the lower frequency band, but we are seeing this pressure going up in the frequency band as more and more applications that require more bandwidth are being brought to bear. So we work nationally and internationally to ensure the proper utilization of the spectrum, and as well as the management of the spectrum asset to optimize its use and to make some of the spectrum available for commercial applications. We work on data standards, at least the space data standards. Our main objective is to pursue interoperability, so standards are critical to ensure cross support, so systems can talk to each other. We work also on advancing PNT policy, positioning and navigation, timing are so critical for navigating in space as well as on the ground, but our mission is in space. So we work with the Air Force as well as many other entities to advance policies that are suitable for very effective PNT services. We are one of the few programs that are located at headquarters, and we do we coordinate with all of the and directorates. But however, we are the one who are responsible for representing and negotiating on behalf of NASA on all matters of space communications as well as technology. We do that because we have a major responsibility. On a daily basis, we support more than 100 missions flying around the globe within the solar systems, and we even have missions that have crossed the boundaries of our solar system, now the interstellar area. We are required, and it's our job to provide 24/7 support to all of these missions at a high proficiency rate. We are talking about 99.9% availability. So I don't know how many of you are familiar with SCAN, but NASA missions, they fly around the globe and within the solar system, and they all have different needs in terms of their command and control, as well as their telemetry coming down to the ground. That's why we've had 3 different types of networks. They vary in terms of capabilities because they support different classes of users. The oldest of which is the Deep Space Network. The Deep Space Network caters to missions that are flying so far away. We are talking beyond 2 million miles, 2 million kilometers, all the way to the edge of the solar system and beyond. We have 3 ground stations located around the globe, phased by about 120 degrees, one from the other, 2 in the upper hemisphere and 1 in the lower hemisphere. providing 24/7 support to all of the mission flying well beyond Earth. They rely on very large antennas. These are our Eiffel Towers, 70 meters large. We have at least 170-meter antenna per ground station. We also have many 34-meter antennas, beam waveguide antennas that do support users at different frequency band. And they have also been used to support emergency situation, like a spacecraft around Earth that's going out of control. The power of these antennas and the electronics is so awesome to recover mission in distress and in emergency situation. So they, as I said, they cater to these missions that are flying so far away, that they are sending very faint signals to the ground. So, protecting the spectrum in which we operate there is very critical, because by the time the signal get down to Earth, it's so buried in noise, and so any interference may be harmful to our operation. So we built the station to be far away from civilization, a remote area, and we have a large coordination zone around these ground stations. The near-Earth network also pretty old, and it caters to all missions that are flying around Earth, collecting science data, as well as other science missions that are looking up in space and doing space research. But for the most part, most of the missions that are supported by the near-Earth network, they fly around the globe in a polar orbit. They collect data, and as they get over the North Pole or the South Pole, they dump their data. That's why the location of these antennas have been optimized to the North Pole, to the Arctic areas, for optimum data collection from all of these science missions. This network provides support for launch vehicle, as well as many other capabilities associated either with human space flight as well as the science missions. We also have the space network, a constellation of data relay satellites that are located around the geosynchronous arc, and they collect data from anything flying underneath. We've discovered in the early stages of Apollo that reliance solely on ground station does not give us adequate coverage of human mission, of human space flight. We had about 25 to 30 ground stations distributed around the globe. And even we had ships, we had airplanes every time we flew a human space flight. And despite all of this, we only had like about 30% coverage. So the concept of the space network came about around the mid-70s, and that relied on having data relay point in space, because from space you can see everything underneath, where the mission can connect to the ground station via that data relay point in space. That was the T concept that has demonstrated its viability to support anything flying underneath the geosynchronous arc in real time. So all of the missions that require near real-time support or mission with low latency depends very much on the TDRS constellation. The last TDRS was launched in 2017, which was TDRS-M, and brought into operation in January 2018. That was the last TDRS. When the concept of TDRS came about, NASA was among the few entities that was building data relay satellites from space. Now we see an explosion in these capabilities. So many commercial entities have deployed system around Earth, be that fixed satellite service or mobile satellite servers. that can do the kind of job that TDRS is doing. So NASA, seeing that there is a potential benefit from using these commercial networks, that is going to move away from a government-owned and operated system in favor of relying on commercial services provided by commercial companies operating in space or on the ground. We see great benefit in terms of cost and in terms of robustness. And this is where we came up with the concept of interoperability. To get support from these commercially provided services, you need to have the ability to communicate with many of them, not just a single network. Because you don't want to be wed to a single network. You want to have the ability to roam in space and get support from any network that's available up there. We look at the future, with a lot of concern. NASA has been asked to commercialize space, and we see plenty of commercial opportunities in the next 10 to 15 years being explored up in space. So we are going to see a lot of businesses moving up and a lot of activities. It's going to get so dense up there that the operation is going to get more complex. We don't think the present way we operate is going to be suitable for the future. We'll need to have to allow our users to have maximum flexibility and be able to manage without human intervention. We are pushing the concept of autonomous operation as well as autonomous navigation, and to build the kind of capability that will allow our users to negotiate access to any network, to any provider's network, be that commercial or any other network, even government-owned and operated systems, on their own, because we cannot afford the overhead associated with the human intervention. And also because of the congestion up there, contention for spectrum and the need for bandwidth is going to grow. As you know, that these providers, they all operate at different frequency bands, and they have different waveforms. So in order to talk to many of them, our user will need to have different COM payload to talk with the individual networks. That's, will take so much space, will require so much power, and, will undermine the mission ability to collect science, because there won't be any room on the spacecraft for scientific instruments. No, we would like our user to have a single COM payload capable of talking to as many of these providers as possible. And we would like to have the kind of capability where bandwidth is no longer an issue. So we have been pushing the kind of technology that will allow us to do so. As you know, the frequency spectrum is in high contention and also is a limited, the finite asset. So we have been pushing way up in the in frequency all the way to the optical range, and that's why the optical communication is taking that strategic value to us. So we definitely have a need for smart systems up there. We need to have the ability, the flexibility to move between waveforms and frequencies, and we need to have the large bandwidths. As well as the navigation, autonomous navigation is so critical. Operating in space is different from operating on the ground. On the ground, a user going at relatively low speed will be within a beam, within the spot beam of a particular provider capability. When you are up in space going at the speed of 17,000 miles per hour, you'll be going in and out of beams. That adds complexity to the technical capability on board to be able to go from beam to beam, hop so quickly that by the time you are getting out of the beam and you are losing that signal. So we'd like to have the kind of capability that will allow us maximum flexibility and robustness. And this is the, our main objective. And now, by moving away from building our own assets and operating our own asset, we are going to free ourselves to focus on advancing the technology, constantly pushing the envelope on the next generation technology. So what are we doing? In 3 different areas. To enable our users to roam in space, we need to have an interoperable environment where my spacecraft can talk to any other provider's assets. So we need to be able to talk to each other. That's why, an interoperable space requires the kind of capability that's working to certain standards. So we need to harmonize the data standards that are being utilized. In the past, we relied on CCSDS, but now we are seeing so many other standards coming from the commercial sector that are also suitable for space-based operation. And so working with these bodies, we have been able to push and to advance so many new standards, from optical all the way to new communication protocols suitable for a highly dynamic environment, such as disruption-tolerant networking and so on. And we started to infuse these standards into our operation. All of our system will be capable to talk to so many providers in a highly dynamic environment. The spectrum, as I said, operating from space, as I said, is different from operating on the ground. In space, the boundaries of the spectrum become so not so defined, and so and also getting support, space-to-space support, presently is not possible based on present ITU regulations. And so we are working very closely with regulatory bodies to ensure that such spectrum is made available for space-to-space operation. And I believe at the next WRC, the World Radio Conference of 2023, we are going to see this item be deliberated there, and we are going to get access to get that space-to-space support. So regulation have always been like showstoppers. When you heavily regulate something like spectrum, you are building walls. And in the past, there have been so many walls between government system and commercial system, scientific activities, commercial activities. We are trying to push on the envelope on technology to ensure that we can stay afloat and tackle all of the regulatory constraint using technology, so such that we can navigate the regulatory environment by relying heavily on flexible and robust technology that can overcome these challenges. And so we have been heavily invested in this kind of technology, all the way to building cognitive system, cognitive radio, that will have full situational awareness of the state of health of all of the channels, all of the networks, and be able to reconfigure the system to the frequency band or to the waveform suitable to get support from a particular provider. So cognitive systems, smart system, are critical for future operation to enable that autonomous operation without having a human in the loop. So I talked about navigating around the spectrum, be able to reconfigure the radio from to a particular frequency band and a particular waveform. And you can see on this chart how the frequency spectrum is used among so many of these providers. And there is no way, if I have to get support from many of these providers, I will have to have a separate radio for each provider. There is no way we can do that. Especially our missions now are getting smaller in size, and I would like to have my communication payload to have a small footprint on the spacecraft. So I'm working along with many other partners on having a multilingual receiver that can operate in a large portion of the spectrum, at least depending on the mission needs and requirement and their data rate. I can select a large portion of the spectrum where my receiver can tune in frequency and also have the flexibility to reconfigure itself to the waveform associated with any provider. This is the research, and the capability is moving forward, and I expect this advanced radio, multilingual radio, to be available within just a couple of years. We are talking something that can operate, over 10 gigahertz plus. So, and this will allow us to talk to different providers and be able to roam in space in a seamless way. The cognitive capability is a work in progress. Also, I'm giving it 2 more years. Cognition is so critical because you really need the system and the platform to make decisions on its own, on which network to access, also on be able to have that dynamic aspect of accessing the spectrum, and to be able to provide better performance and more reliability. And security is critical in here, because really with a cognitive system, you'll be able to ride over so many issues, providing more security and resiliency. And so we are very hopeful that the capability will be brought into operation by the 2024 timeframe. Definitely, it's our objective that once we have the capability in place to share it with the commercial sector, as we do with all of our technology. We transfer our know-how and our technology to other entities, in particular to the commercial sector. There are plenty of challenges ahead of us, but I'm very confident that we are going to get there. The technology from a processing power has gone a long way. We have more capability now, more processing power, and our mathematical analysis, mathematical models have advanced so well to be able to build the cognitive system that can operate in real time and meet the mission needs and the interoperability requirement I talked about. Comes optical, and I know this is what this the whole workshop is all about. We are great believers in the technology. We've started exploring laser comm since the early 2000s. We were pursuing this capability primarily for deep space, the Mars Reconnaissance Orbiter, but then we dragged our feet a little bit. We were working with other government agencies to advance the capability and relying on other government agencies to push the envelope on this technology. When other government agencies did not accomplish their objective, NASA stepped in to take the lead on building the kind of comm payload that are suitable for space communication. In 2013, we had a mission called GLADY, and we had a payload, an optical payload on board, a 10 centimeter. It was our first generation laser payload that we had on board. And from a cislunar orbit around the moon to Earth, we were able to transmit 622 megabit per second using a small aperture ground station. A telescope of about 4 elements. When arrayed together, they give you the equivalence of an 80 centimeter telescope. With that, we were able to accomplish the 620 megabit per second. Please remember that the laser power was, a fraction of a watt that we were using on board the LABI mission. The most surprising thing about that demonstration, that experiment, that we were able to have instantaneous acquisition. Optical links and laser links, they have a very narrow beam width. It's a pixel thin beam. So we were able, we were worried, are we going to be able to acquire, will we be able to align the sending and receiving entities beams, in a short period of time? We demonstrated we could. And that has governed, our approach to optical communication. It's definitely enabling capability, but NASA needed to do more demonstration to get familiar with the technology and how to operate it. While we demonstrated something from deep space to Earth, but we still had to demonstrate something from data relaying capability from a geosynchronous arc to support a NASA mission going very fast. From the moon to the ground, the ground station was stationary. Now, if you are to support something flying in space, you need to make sure that you can have that beam, that alignment of beam. So we have been working very hard to have to demonstrate this capability and to acquire the experience in operating laser communication flying in space. We have a mission called the LCRD. It's a payload, actually. It's done in partnership with many other NASA entities, as well as with the US Air Force. And we are flying this payload on board an Air Force spacecraft that's going to launch in early next year, in 2021. Two optical heads, each one is 10 centimeter, capable of supporting anything underneath. So we'll be doing a lot of that to get the comfort level needed in operating such systems. At the same time, we are working on a user's payload, also another 10 centimeter. It's called Illuma. It will be on the space station, and it will be deployed in 2022. And we are hoping that with this capability, we'll be able to see how flexible can we be by transmitting space through a data relay point in space, or we can come directly to Earth and get that familiarity with laser communications. At the same time, we are looking at the other NASA missions, small payloads, small spacecraft like CubeSats that are flying around the globe, and some of them are going into deep space and collecting so much data. So we have an experiment called T-Bird, where we'll be demonstrating 200 gigabit per second from LEO to Earth. We expect this to fly around the end of 21, but much of our experience, and experiments will be conducted in 2022. We are very hopeful that this will be a very successful demonstration. Much of the technology there is we bought it off the shelf from the commercial sector, with the exception of the optical payload that being worked by one of our subcontractors. In addition to that, the human spaceflight was interested in this kind of capability, and we have a technology demonstration that may go operational once demonstrated on board the Orion spacecraft in support of the human spaceflight. We are very hopeful that this will usher a new era in the human spaceflight by having the kind of streaming video and large bandwidths available for communication with our astronauts, and also get them the same quality of life they have enjoyed on Earth by, having that bandwidth, probably be able to teleconference and get all of the TV channel, watching the latest sport games and so on, without having the bandwidth be an obstacle. This is definitely critical to move into the future, and the gateway I don't know whether you've heard of the NASA Gateway. NASA had decided to have a permanent stay and in deep space, and we are definitely going well into deep space, but we are establishing a point in a cislunar orbit called the Gateway, where we conduct a lot of experiment critical to moving us way into deep space. Having that permanent presence in deep space is so critical for our exploration program. We need to keep on pushing the envelope on the exploration and go as far as we can go. We are looking at optical communication to become the main backbone of communication between us and all of these activities by the end of the 2020s. Not forgetting the benefit of optical communication to deep space. It's so critical, in terms of the swap value, the power, the volume, and the bandwidth, how much data you can accommodate on a small payload from deep space. As we go into, deep into space, a COM payload, if it doesn't get bigger and bigger, it's limited in terms of the data that it can provide. Just to give you an example, the Voyager mission that has gone beyond the solar system only sends data at the 100 bit per second rate. So you really takes us forever to collect enough data to make the kind of observation we need. And if we are to build the COM payload that are needed to provide much larger communication rate, data communication rate, the COM payload will become so huge and becomes a problem, because then it can drive the cost of the mission, and such that the mission doesn't have enough room to do science. All it does is, do COM, and that's not the purpose of the mission. All of our mission's main objective is to collect science, and I don't, NASA and SCAN in particular doesn't want the COM to be a burden. So we are working on miniaturizing the capability and make it more robust and more capable. That's why optical communication, it can provide, at least 1 up to 2 order magnitude better performance than RF in terms of swap value. So this mission is going to fly in 22, and it's on board a spacecraft. We are calling it Psyche. It's going to Psyche, and hopefully we'll gain a lot of experience and knowledge on how to operate such system in deep space. So as I said, communication capabilities, have seen so much evolution. We still are, pushing the envelope on the conventional microwave capabilities, and we are reaching the boundaries because, in terms of capabilities, as you need more data, as you need to go much further, your antennas are growing, and from centimeter to the tens of meters, and you are, and we talked about the spectrum, how it's getting saturated, while the appetite, our appetite, not only that of NASA, but the commercial sector for bandwidth is growing. You can see all of the commercial applications now, they are requiring more and more bandwidth. In the past, we are no longer talking about baud rate of 4,800 bit per second. We are talking gigabit per second and beyond. So the spectrum is becoming so not only congested, it's becoming, how to say it, a showstopper. That's why it's a natural progression to go to something a little bit more capable, and where the bandwidth is still not a problem and can provide you a better value and a better return on investment. And we have seen, we are building on so much capability built for terrestrial application to advance the capability up in space. So optical communication is the natural progression, moving us from the conventional way we have been doing communication into a new paradigm. Does not mean the conventional way is going away. It's going to be both are going to piggyback on each other's capability, and the things have to be managed together, not one independent from the other. And the future looks brighter as we explore the quantum domain. Definitely, quantum communication is now, it's a strategic objective, but in order to build the quantum network, and quantum network are going to be so capable, enabling us to do a lot of things that, that are not, how to say it, that are, a major challenge now, from security to processing power, and to things like enabling better data, sensor fusion, distributed quantum processing, and so on, to encrypted communication links. So quantum communication provide that, in addition to so many other scientific objectives that can provide better accuracy and better sensitivity. So we are pushing in this direction to evolve into quantum networks in the future, but they all rely on a single photon. So you're talking about photon. So that's why optical communication is so critical to enable the future quantum communication capability. Quantum will ride over optical capability. And so in advancing our quantum objectives, we've made a deal. We entered into partnership with NIST, National Institute of Standards, as well as NRO, because it's a sister agency that operates in space. So we are looking and demonstrating such a capability, to move data between continent, even transcontinental to the United States. To be able to send encrypted data, entangled data from one point to the other at extremely high resolution or high data rate. This is something in the work. It's a proposal. It is not fully funded. We are still working on expanding the partnership with other space agencies, with other government agencies, and I would like the partnership to include the commercial sector. We all have to move together. The lines and the wall that built between government and non-government, and commercial, they need to come down. We all need to work as a single community of interest to advance the capability and the technology. Advancing these capabilities is a must as we keep on, wanting and more bandwidth and more security. The more we rely on the electronics environment and the information environment, the more we are going to need to advance the capability to a more secure, robust, and capable set of capabilities. So hopefully we'll be able to build to a largest partnership and work all together to advance the country's objectives, not only that of NASA or the individual interest of specific agencies. So again, the future looks bright. We have declared the 2020s as the decade of light, because that's the decade that where optical communication is going to mature and be infused into operation. We would like as much partnership and to expand our partnership with the commercial industry and with everyone to keep on moving forward and build these kind of capabilities. Thank you for listening to me. I would have wanted to have had this thing face to face to be able to respond to your questions. But for now, all we can hope is that COVID-19 will be behind us and we'll be able to meet again. Thank you.